Carbon fibre wheels, the ultimate upgrade that makes any bike look cooler and ride faster. But how are the latest carbon wheels made? And what makes them special? Well, behind me is a factory that does just that. So we're going to find out today how the latest wheels are designed, manufactured, and also stress tested to see how strong they are. Oh, and if I look tired in this video today, it's for good reason. That's because we've been in Taiwan over a week now. I first went to the Taipei bike show, and then we rode the entire length of Taiwan, north to south, through the mountains, Connor and I, using these very wheels. And that's why they're looking a bit dirty. But these are the new Vision Metron RS, the latest and greatest wheel from Vision. So let's go inside and see how they were made. So the process of developing a new wheel starts in here for Vision FSA, where they employ over 60 engineers. Now, they work across different things, so they also work across handlebars, the chain sets that the company makes, but several of the engineers work on the wheels. Now, with the new wheel, we've got some of the design process I can show you here. So the carbon layup has been inputted into this software here. And you can see this is a cross-section of the new rim, which we will go and see shortly over in the carbon area of the factory. But this software maps the carbon layup. So you can see every white line is a layer of carbon fibre that's going to be put together in the final product. So you can see in the rim bed here, there are 2 layers there. And then you can see that there's also a layer coming around here, and then several layers, particularly in the area here that needs to be strongest, where you have the tyre wheel interface. Once the shape and the layup has been determined for the wheel, they can then input it into this software here, which performs a finite element analysis of the wheel. And that allows them to model the stiffness characteristics of the wheel to see, well, how strong it is under load. So for example, here, we can see that by applying a static load to roughly this point on the wheel, you can measure the deflection at different points in the wheel, so that we can see there is 6.2 here, and then much less deflection on the opposite side of the wheel there. Now, one of the ways in which they've been able to make these new wheels stronger is by playing around with finite element analysis. And what they've done with this particular wheel is, well, one of the key things is make the hub flange larger, and it's a complete redesign on things they've done previously, which has improved stiffness, and also the use of the carbon spokes. But more on that later, where we're actually, or hopefully, going to go test and see how stiff these wheels are in real life in the lab. The other key aspect of a performance wheels design is its aerodynamic performance. And that is done not here in Taiwan, but over in Vision's USA headquarters. Now, the way that's done is a kind of twofold process. The first thing is computational fluid dynamic studies, which are simulations run on a computer in a similar way to the finite element analysis we've got here. And that can model the fluid dynamic behavior of different rim shapes. And that helps decide the rim shape they want. Also things like the bladed spokes. The second component of that aero development comes in the form of validating those shapes in real life in a wind tunnel to see how they actually perform. But once the aerodynamic shapes have been decided and settled upon, it's back to here to make those shapes become a reality. So the first step begins with the raw material, which is carbon fibre. Now, carbon fibre is made by a select few companies in the world. Now, it arrives in pre-preg form, so that is sheets of carbon fibre of different types and weaves, and it's impregnated with resin. That's what the pre-preg means. Now, this needs to be kept at very cold temperatures, because if it's left outside, the moment it's taken out of the freezer, the clock starts ticking and the resin that's in this carbon starts to cure. The carbon fibers themselves, they're not temperature sensitive, but it's the resin that's important. Let's have a look in here. It is so cold in here. It's so cold in here. You have to get out. It's like -20. So it's really important to combine different layers in different orientations so that you have strength in multiple directions. And so what you would do is, you can see that the strands in this layer go that way, and so we would take another piece and put them cross-linked over that to give it strength in both directions. And the way in which they do this is they take those huge sheets of carbon and then they cut them out with these CNC profilers here that are basically cutting out a huge jigsaw puzzle of different carbon pieces, which are then going to be put together to make the wheel. Using a machine to cut out the carbon on the sheets like this is far more efficient and really helps not waste material, which is really important because this stuff isn't cheap. Now, in this part of the factory, they're laying up the rims into the moulds. Now, I've just come through a double door situation here, a little bit like a sort of airlock. The reason for that is because the climate in this room is carefully monitored and controlled, and that's very important. Now, if it were too humid in here, there'd be too much moisture in the atmosphere, and that can affect the carbon. If you have too much moisture in your raw carbon, then as you heat it up in the moulds, it can create voids and make it structurally weaker as that water evaporates during the high pressure and temperature of the autoclave. If the temperature is too high in this room, then that also affects the carbon. You've already seen that the carbon has to be kept in a fridge so that it's nice and cold. If it's too warm, that resin starts to cure. Now, as for the construction of the actual rims themselves, that's really interesting. These rims are constructed of three core components. So I've got a cross-section of a piece of rim here to show you. So this bit here is the inner core. That forms that area of the rim and the aero shape on the outside. You then have this flatter section here, which has been wound together, and that forms the rim bed and also the hooks on the outside. And the final piece is a layer of carbon that's put around the outside, which kind of just holds those two components together and just binds everything and makes it strong. Now, the inner core part of the wheel is made from 18 individual pieces of carbon. It's really important to lay them up by hand in this way so that you can maximize the material and also make it strong where it needs to be by alternating the orientation of those different fibers. The rim bed part is made from 4 different layers, which then goes on top of that. And then you have the final outer layer. Now, all in, the time to do this, you're talking about 30 minutes to lay up a single wheel. You're then talking 20 minutes to wind this together. That's done by a machine, not by hand. And then 10 minutes of assembly here before it is ready to be cured. So that rim bed part of the wheel that I showed you before, I said that was 4 different layers. That's because it is 4 different layers, but of one piece of carbon. But that one piece of carbon comes off one of these rolls. You can see it's very thin, and the machines behind me are then sort of knitting, rolling that around a mandrel to get it into that shape.
Once laid up and placed in the moulds, the wheel rims are baked in huge ovens at high temperature and pressure. Each oven can do 4 rims at a time. The high temperature and pressure is required because it allows the resin to run freely as a liquid and flow through the carbon structure to uniformly distribute itself throughout. This creates a strong rim. After baking for 40 minutes, the wheels are cooled.
And then they come out round on this huge belt behind me where the guys are taking them out of the moulds. You can see I've got one here. At this stage, it's got quite a bit of flash still left on the mould, so they're cleaning them up a little bit and then sending them down the belt so that, well, the next stage can happen. It's quite heavy, this, at the moment, as it's just come out, because it's still got the bladder inside it that's helped push the carbon outwards and create that outward pressure. But the surface finish on it, say that's just come out of the mould, that's pretty good. I'm impressed by that. So fresh out the mould, the next step is to remove this inner channel so that you can remove the bladder and the mandrel that's inside here that's given it its shape. And that's done with that machine there. What that does is it carefully and very quickly applies two very accurate cuts along here so that that inner channel can be removed. Here's one I made earlier, and you can see the channel just comes out like that. And then underneath this is actually where the mandrel goes in here. Now, I can't show you that mandrel, what it's made of or how they remove it, because that is top secret. But the way in which they're doing it and what they're using here is very special, and it enables them to have an exceptionally high tolerance for this rim bed shape and also the tyre bead interface on the side there, which is absolutely crucial for a tubeless wheel. The remaining flash and bits from the moulding process are removed by hand. You can see the ladies behind me here using files to make sure there are no sharp edges or excess bits of material. The bladder is also being removed here as well. As you walk through the Vision factory, their racing heritage is everywhere, and rightly so. They've got a lot to be proud of. I've just spotted something very cool here. So there's Mark Cavendish's bike for his stage win record at the Tour, but what I really want to do is try out these extensions. So these are Primoz Roglic's custom Vision extensions that he has on his TT bike, right? I'm just going to try and fit into there. That's a tight squeeze, that. And that doesn't feel very comfortable to me. I think Primoz has got little arms, certainly smaller than mine. But Wout van Aert's are here, so I'm going to try those ones as well. Right, Wout van Aert's TT. Oh, that fits like a glove, that. That fits me really well. I'm basically Wout van Aert. I don't really know, I haven't really got anything more to say. But the rims are just one part of the wheel. You also need hubs, and that's what this part of the factory is making. Now, the first bit that I can show you is the Freehub body. Now, this is made in a two-part process. The first step is to make this, which is die cast. So it makes this large, chunky Freehub by just injecting liquid metal into a mould. The next step involves this large CNC machine just over there, which is a CNC lathe and milling machine, which is able to surface finish this part, but also bore out the excess material to make it nice and light. So once it's been in this CNC machine, all that liquid, by the way, is cutting fluid and coolant. But once it's been through the machine, it looks something like this. This one is a SRAM Freehub body, and this is a Shimano one, but you get the idea of what it will look like. This is also much lighter. So the new Vision PRS hub has a 72-tooth ratchet in it, and what enables that are these sprockets or ratchets that I've got in my hand here. They're made in these CNC lathe and milling machines. It's a two-in-one machine. There's one there, there's one there. There's quite a few of them in here. But seeing these precision-made ratchets come out of those machines, there's something really satisfying about it. It's like a sort of Swiss watch or something. What's really cool is the tolerances on these have to be absolutely spot on. And so to test that, they've got these gauges. They're called go gauges and no-go gauges. So this is the go gauge. It has to fit into this gauge. So if I align that up and put that in, look at it. This is satisfying, this is. Look at that. Just fits in perfectly and goes through. Look at that. So the part of the factory in now is where the hubs are assembled. Now, this is the hub shell of one of the Vision hubs, and this is the Freehub body that will go onto that. The way these are made are they're forged and then they're surface finished in different ways. So this one's been anodized, others are sandblasted and then anodized. But the next step before the assembly can take place is what's known as rolling, which is what these machines are doing here. So that bit goes inside the Freehub body and also inside the hub shell, and it rolls the inside out so that the tolerances are absolutely perfect for when the bearings are going to get pressed in, which is the next step. You can actually see in this Freehub body here, we've got the bearings have been pressed into place, but they're pressed in with what's known as an interference fit. And for that to work, so that your bearings have a nice long lifespan and work properly, that interference fit needs to be absolutely perfect, which means the tolerances need to be absolutely perfect, hence the need for rolling. The bearings are pressed in place using this press and these different size drifts depending on the hub that's being manufactured, but something very satisfying about new bearings that are fresh, just so nice and smooth. But they don't just have a joker like me saying that the bearings feel smooth and are good to go. They actually have a machine here which measures the torque in the hub of those bearings to check that the quality is there and then they're properly aligned and there's no extra resistance in the hub. So I've got the different constituent parts of one of the new V1000 PRS hubs here that's on the new wheels. And it's really nice having all the bits together, and I can show you how they go together. So the first thing that goes on is the end caps. So there's one on each side. You can see the bearings have been pressed into place in this one. So it's got nice ceramic bearings in there. Nice. Then we have the nice coil spring. And then got grease on my fingers now. The nice thing about these hubs as well now is that the Freehub body can just be pulled off without tools, and you can access the bearings and service the hub if you need to. Clean out those really nice ratchets. Nice. Now next comes the building of the wheels, and so what you can see here is our hub shells pre-laced with the spokes, but these aren't any ordinary spokes. They're now carbon spokes on the new RS wheels. Now, that saves around 100 grams per wheel, and the reason for that is simple. A normal steel spoke weighs over 4 grams, about 4.7 grams, whereas this one weighs about 2.3 grams for a spoke. I also like this kind of like master spoke that has some writing on it. It looks very smart, but this lady here is lacing up the wheel and getting it built using a torque driver that's got a pre-selected torque so that every spoke has the same torque on it. However, it's not finished yet. It needs to be finely tuned and made sure that it's completely true and that the tension on each of those spokes is absolutely perfect, and that's what they're going to do over there. It's very important to measure the spoke tension on each one to make sure the wheel is built to the highest quality, and they tell me that they do this on every single wheel to check that it is absolutely spot on. They don't just eyeball it, whereas some factories I've seen, they don't necessarily check every single wheel. Pretty cool. This is where the fine-tuning of the wheel truing is taking place, and the tool of choice for a professional master wheel builder is the professional wheel alignment gauge from Park Tool. There you go. Of course it is. As part of all the quality control that's going on here, every wheel is tagged with a barcode and a serial number, and it has all the details in it of the truing process and the tension that was on all the spokes, and then that gets scanned and put into a computer. So there's a record of it. So if anything ever does go wrong with your wheel, they have a record of everything that happened to it during the production and who made it, so they can get put on the naughty step if it wasn't right. I'm only joking. As a nerd, this is probably the coolest room I've ever been in, and the reason for that is because it's filled with lasers. Now, they're using these lasers to etch on logos and certain graphics on the hub shells, but also some of the rims as well. You can see the Vision logo being lasered on to this rim I've got here. It's is so cool, but also really satisfying to watch. The graphics on the new Metron RS wheels are done in a different way. So they're actually done in a very, well, special and clever way, in that it's able to be done out the mould and they're simply polished on the carbon. And this actually saves quite a bit of weight, about 20 grams per wheel. Cool. But even after the wheels have been built and calibrated, there's still an important step, and that happens here. This is best described as a torture chamber for bike wheels. So first up is this machine behind me. Now this is designed to fatigue test the wheel as it hits bumps in the road. This is an ISO test that all bike wheels have to satisfy, except they up the ante on it. So what you've got here is a drum that's got bumps in it, and then this is a huge flywheel weight, which is 60 kilogram load applied to the wheel, and then it's spun at, for the ISO test, 25 kilometers an hour. However, Vision do it at 40 kilometers an hour, and that's to simulate your wheel hitting bumps in the road at speed. Now, the ISO test runs for about 800 kilometers. However, Vision do their rear wheels for 2,500 kilometers, and it has to satisfy that stress test. See it in action. This is really cool because there's more lasers. But this time, the lasers are measuring the deflection of the wheel laterally. And if it moves more than 2 millimeters, then the machine shuts off. And at that point, it's deemed that the wheel has failed. However, the new wheels are said to be even, well, stronger than the previous ones, more durable. And the engineers here were telling me that the reason why they think that is a couple of things. So now they're wider and they're using 28 millimeter tires, which can absorb more of that energy. But also they reckon they're seeing better durability because of those carbon spokes. The carbon as a material is just a bit better at vibration dampening and absorbing that energy. And so as a result, they think that's why. Here's another stress testing machine. This machine I'm going to call Tadej Pogacar because it has a 65 kilogram load on it, and it's driving the wheel at 500 watts constantly. And so what this one's doing is driving the wheel from the hub, and so it's not being driven from the drum at the bottom, so that's a bit different. And the other thing is the machine is able to rotate, and it stays 5 seconds there, 5 seconds in the middle, 5 seconds back the other way. So it's simulating what would happen if a rider was sprinting hard or going around corners and placing that slightly different load through the wheel. And again, we've got a laser there measuring the deflection, and if it becomes more than 2 millimeters, the test is over. On to the next bicycle wheel torture device. And this, as you probably recognise, is the HT8085HB, otherwise known as the UCI's impact test. Now what this does is pretty simple. You take a wheel with no tyre on it, and then you drop this weight on top of it with these silicon pads on here, and it has to survive the impact. Now, the UCI test stipulates that it has to survive 40 joules of energy when it hits it, right? But Vision like to take this up a notch. They like to up it to 100 joules. And they tell us that they've actually done some competitive testing on wheels and have found that, well, some wheels don't really survive even beyond 70 joules. I want to see it take some impacts. Let's do this. And this is probably the greatest moment of my life because they've just told me that I can press the button. How much was that? 100? 40.
It's a UCI standard.
That's the UCI standard. Passed. Right. 100. That was quite violent. Has it survived? The wheel is apparently fine. The sound, they say, is very different when it fails. Okay. They've let me put it up to maximum, which is 120 kilojoules. The machine won't go any higher. And that is 3 times the UCI standard. So let's see.
Pass.
It's a pass. I hope you found this look at how wheels are made as fascinating and interesting as I have. If you have, then please give it a thumbs up and subscribe to the channel, and well, share this video with your friends, if you've got any. Massive thanks to Vision for giving us the access inside and seeing everything. It's been great. I'm going to fly home now, so, well, back to England. Love you. Bye.